Okay, today we're very excited to have Achilleas Porfyriadis. He received his PhD from Harvard before moving to Santa Barbara for a postdoc. Now he's back as a member of the Harvard Black Hole Initiative, and today he's going to tell us about extremal black holes. So take it away.
Right, thank you. Thanks, Dan. So let me share my screen. So even though we're on Zoom, this is still a seminar, not a big conference talk. So I encourage people to interrupt me at any moment and ask, whatever question might arise. So my talk today is titled Extreme Black Holes, Anabasis and Accidental Symmetry. And so it will be roughly divided into two parts. In the first part, I will explain what Anabasis is. And in the second part, I will explain what is the accidental symmetry that we've discovered. All right, so let's begin. And so we can begin by reminding people that ADS2, two-dimensional anti-de Sitter space-time, is universally arising near the horizon of extreme and near extreme black holes. Sorry, let me go back. Yeah, so this is true. Is there a question? No, okay. So this is true in the prototypical example of ADS2 cross S2, which is also called the Bertotti-Robinson universe. Bertotti-Robinson was discovered independently as this solution, which was interesting for cosmology. And it is simply just ADS2 times cross S2. So the TR part here that you see is ADS2 in so-called Poincare coordinates. It's an exact solution of the Einstein-Maxwell equations. But it is also describing the near horizon geometry of an extreme and also of a near extreme Reissner-Nordstrom black hole. And so this is a prototypical example, but it's a pretty universal phenomenon, and in particular it applies even to the astrophysically relevant Kerr black hole, that near its horizon, the geometry there as well is ADS2 light. So you can see the same ADS2 appearing here. Of course, it's more complicated in the rotating case. There is a non-trivial vibration over that ADS2 that's angle dependent. In this talk, we won't talk about the Kerr case at all. I just wanted to flash this so that you have at least in mind that this ADS2 arises everywhere, including up in the sky for observations of black holes which are near extremality. Okay, so and there is a general theorem basically that you can find in this paper, which proves this statement for a large class of theories in many dimensions. And I want to emphasize again that these are both near horizon approximations of the spacetimes that describe asymptotically flat black holes and exact solutions of the corresponding Einstein equations as well. All right, so the talk is divided roughly into two parts. The first part is the Anabasis part, which is based on this paper with Shahar Hadar and Alex Subsaska. And the second part is about the accidental symmetry. So let's begin with part one. So the motivation for this, for defining this Anabasis stems from some physics statements that you find in the physics literature, which go under the slogan that ADS2 has no dynamics. And so, as far as I'm concerned, the oldest appearance of this type of slogan in the physics literature is this paper, and you can see here in the abstract highlighted the statement that all finite energy excitations of ADS2 cross S2 are suppressed. Then later on, when the near horizon of extreme Kerr and near extreme Kerr was discovered and studied in the context of the so-called Kerr-CFT correspondence, a similar statement was made, backed by correct calculations, of course, which was elevated all the way up to the tidal, where you can see here no dynamics in the extremal Kerr throat. And since there are also mathematicians in this audience, there are papers that some mathematicians have been writing, which are directly inspired by this physics literature. Here's one, for example, by Greg Galloway, where he's talking about this rigidity theorem of ADS2 process. So, but let's take a step back and think about the wider picture. So what do these slogans mean? What these slogans mean is that backreaction in asymptotically ADS2 spacetimes is problematic. So think, for example, of the following question. You begin with a linear solution for a simple scalar field on ADS2 cross S2, and you ask yourself, does the solution of that linear Klein-Gordon equation on ADS2 extend to a nonlinear solution of the full Einstein-Maxwell scalar theory or not? So for this type of problem, you need to take into account backreaction. You need to let your scalar field phi backreact on the geometry, generate metric perturbations, and evolve non-linearly the Einstein-Maxwell scalar equation. And so the answer to that question is no. That's the part where backreaction is problematic for ADS2. But it's no if you insist on obtaining solutions that are still asymptotically ADS2. So ADS2 has a time-like boundary. So for example, if you impose Dirichlet conditions on the time-like boundary and then study the backreaction problem, you will find that that's not consistent, that the backreaction destroys that boundary, basically. It doesn't respect the boundary conditions that you're imposing on the ADS2 boundary. Okay, so that's the sense in which ADS2 has no dynamics. But think now of the same ADS2 cross S2 geometry as the approximation to the near horizon of a Reissner-Nordstrom black hole. So now we are in an asymptotically flat spacetime. And there, from physics perspective as well, as from very detailed numerical evolutions, we know that backreaction makes perfect sense. So if you start, let's say, with a scalar field phi, which is of order epsilon to the 1/2, and we think of it as being put on the extreme Reissner-Nordstrom spacetime. So there is a profile of that scalar field in the near horizon region. It's of that order. Does it, when you consider backreaction, does it extend to a nonlinear solution of the Einstein-Maxwell scalar equations? And the answer to that is yes, it does. And what it produces, what's the endpoint of that nonlinear evolution? Generically, the fully backreacted nonlinear solution is just a nearly extreme Reissner-Nordstrom. So suppose you began with an exactly extreme, put the scalar field of order epsilon to the 1/2, you end up with a near extreme Reissner-Nordstrom, which has a charge to mass ratio given by this square root. So this has been verified to numerically, for example, in this paper, in fact, very many details. And it's also expected from physical grounds. So we know, therefore, that the connection of ADS2 to the asymptotically flat region of a black hole does allow for a consistent backreaction to take place. So in this first part of the talk, I want to understand how that happens and what are the correct boundary conditions from the point of view of the ADS2 cross S2 that is in the near horizon region. Okay, so let's begin. So here's our background again. The entire talk will be about the spherically symmetric case, so just Reissner-Nordstrom and Bertotti-Robinson. I'm not going to talk about Kerr or any other solution in this talk. So here's again the Bertotti-Robinson solution, spherically symmetric solution. This is a metric, this is a gauge field that supports it, and we're in Einstein-Maxwell electrovacuum situation. And let's consider also only the spherically symmetric sector. Again, the entire talk will be in that spherically symmetric sector. So what are the perturbative solutions around this Bertotti-Robinson background within spherical symmetry? So the solutions, that is metric perturbations and gauge field perturbations, can be fully characterized by the h theta theta component to that perturbation. So there are other things turned on, of course, but the h theta theta is very convenient because it is gauge invariant for this linear problem, and therefore it contains the entire physical content of all of the linear solutions. So we see here that therefore the solution is a 4-parameter family of solutions. The 4 parameters here being phi 0, A, B, and C. So this is already kind of surprising, because if you did this exercise in Reissner-Nordstrom, you would get only a 2-parameter family of solutions, which is what you would normally expect from by thinking about Birkhoff's theorem, right? So we know that there's Birkhoff's theorem, and that within spherical symmetry, all you can have for Einstein-Maxwell is Reissner-Nordstrom black holes. And so if you solve this linear problem not around Bertoldi-Robinson but around extreme Reissner-Nordstrom, you would find a 2-parameter family of solutions, which would be the 2 parameters being the deviations in the mass and charge of the black hole. So here there are 4. Why are there 4? And that's one of the somewhat surprising things. But I should say this is not inconsistent with Birkhoff's theorem, because Birkhoff's theorem is a local statement. So all it says is that all solution is in an open neighborhood can be identified with a region of Reissner-Nordstrom, and here we are in the near horizon region of Reissner-Nordstrom black hole. So we haven't found a problem with Birkhoff's theorem, but at this linearized level, we have found a larger class of family of linear solutions. So we have this 4-parameter family of solutions, all being traced in the h theta theta component, which is gauge invariant. The first parameter phi 0 is very easy to understand. So what it does is it just corresponds to the overall rescaling of the scale here in Bertoldi-Robinson. So there's only one scale here, so this m. If you send m to the m plus delta m, this is a parameter shift, which does correspond to a linear solution with phi 0 equal to 2m times delta m. So this is easy, and for the remaining of the talk, I will only consider the rest of the solution here, A, B, and C, which collectively we'll put in under this variable phi. Okay. So let's look at this phi, and let's talk about Sl2 symmetries. So the background, the Bertoldi-Robinson solution, because it is ADS2 cross S2, enjoys an isometry group which contains Sl2, so special linear conformal transformations. So Sl2 isometries of ADS2 associated with the ADS2 factor are given here. So the first one is time translations, second one is dilations, and the third one is called special conformal transformations. So these are exact isometries of the background of Bertoldi-Robinson. This linear solution phi breaks these Sl2 isometries. So if you act with Sl2, you don't get back to the same solution, but you do get back to S solution, because Sl2 is an isometry of the background. So what Sl2 does is it basically rotates this ABC vector. Okay, so that's what Sl2 does, but there's an invariant. There's a Casimir, which is mu here, which is called mu. So b squared minus 4ac is actually Sl2 invariant. So you can think of this as basically like the L squared in angular momentum terms from quantum mechanics. Also, this mu can be thought of as a charge associated with ADS2 in the ADM sense. I'm not gonna explain how this is, but this is true. So there's that invariant Sl2 invariant charge, whereas otherwise ABC solutions get rotated into each other by Sl2 terms. And so if you do want to rotate solutions around, when mu is equal to 0, a good reference would be to set phi equals to 2r. Whereas when mu is positive, a good choice would be to rotate things to the solution phi is equal to minus square root of mu times RT. All right. So the other thing I want also want you to make sure you notice is that these Sl2 breaking solutions phi, unlike the phi 0 solution, are not asymptotically ADS2. So as you can see, they all grow near the r is equal to infinity boundary of ADS2 linearly with r. So they don't fall off at all, actually. Okay. So let's understand what this mu does. So Bertotti-Robinson, the background, arises in two physically distinct ways as the near horizon of Reissner-Nordstrom near extremality, towards extremality. And the two distinct ways are basically two different scaling limits of Reissner-Nordstrom. So the first scaling limit can be described as follows. You begin with exactly extreme Reissner-Nordstrom with Q equals to M. You shift the horizon such that it's located at r is equal to 0, and you use scaling coordinates such that exactly extreme Reissner-Nordstrom takes this form here. So this is exactly extreme Reissner-Nordstrom with the horizon shifted to r is equal to 0, and there is that scaling parameter lambda in the solution. So that's a one parameter family of coordinates for Reissner-Nordstrom, for extreme Reissner-Nordstrom, which is helpful for taking this first scaling limit. So suppose now that you do take lambda to 0, at order 1, you get the Bertotti-Robinson in the Poincare coordinates that we've been working on so far. So this equation, as you can see. Now, because both of these are exact solutions of the nonlinear Einstein-Maxwell equations, we know that the order lambda corrections in the scaling limit would define a linear solution around the Bertotti-Robinson. And that's what indeed happens. And what linear solution is this? So you can look here at the h theta theta perturbation. It is just 2r in this case. So this is the solution that you get by these means. So the Sl2 breaking mu equals to 0 solution that we called phi is equal to 2r previously, we'll now call the Poincare Anabasis solution. And why Anabasis? So what Anabasis means is basically an ascent towards a low gravity, a low strength gravitational field. So since this 2r solution, all that it does is it begins to build the asymptotically flat region of the exactly extreme Reissner-Nordstrom black hole, we call this the Poincare Anabasis solution for the mu equals to 0 case. So this solution has mu equal to 0. And therefore we have just learned that the nonlinear solution that you obtain by starting from this mu equals to 0 perturbation to r of ADS2 crosses 2, if you allow it to be fully backreacted in the context of Einstein-Maxwell theory, is just the extreme Reissner-Nordstrom black hole. Okay, so that's the first lesson. That's what happens when mu equals to 0. But there is a second limit, a distinct physical limit that you can take for Reissner-Nordstrom to get to Bertotti-Robinson as well. So this is the second limit which you can take as follows. So suppose you don't begin with q equals to m, but you have q equals to m times this square root, under which you have this lambda squared term. And then again, let's imagine that you have shifted the horizon to be at rho is equal to 0. So in these coordinates, the Reissner-Nordstrom black hole, generic Reissner-Nordstrom black hole, can be written as follows. So this is just Reissner-Nordstrom written in a one parameter family of coordinates where the horizon has been put at rho is equal to 0, and there is that parameter lambda, which we're going to use to take the scaling. So again, in these coordinates, if you take lambda goes to 0, what you recover at leading order is an exact solution of the Einstein-Maxwell equation, this guy here. So this guy here, even though it doesn't look like it, it actually is Bertotti-Robinson. So locally, it is the same solution. And therefore, again, because both of these are exact solutions of the nonlinear Einstein equation, the order lambda correction in the scaling limit will produce a linear solution around this Bertotti-Robinson. And so here, if you look at the theta-theta component of this guy here, you will see that we get the solution H theta is 2 times rho plus kappa. So I have said that this line here is actually a Bertotti-Robinson. So let's actually see how that is. Well, the way to see it is to display the coordinate transformation, say back to the Poincaré coordinates. So if you transform those tau rho coordinates in this metric into TR coordinates by this transformation, and you accompany it by the appropriate shift to the gauge field, so not a gauge transformation here as well, then in TR coordinates, we get back to the Bertotti-Robinson that we were using before in Poincaré coordinates. So that's the sense in which we have shown that the background is the same. And the perturbation then, this 2 times rho plus kappa for the H theta component, gets transformed to this minus 2 kappa times RT. So as expected, of course, we got one of the solutions that we were calling phi before. But which solution is that? That's an Sl2 breaking solution. That's also expected. That we were identifying as a reference in phi, where phi is equal to minus 2 kappa times RT. Now this solution has a non-zero mu. So square root of mu is actually 2 kappa here. So what we learn is that the Sl2 breaking solution with mu not equal to 0, which can always be brought into this by an appropriate Sl2 rotation into this minus 2 kappa RT solution, we learned that this mu positive perturbation of Bertotti-Robinson, when you let it fully backreact on the background, what it does is it begins to build the asymptotically flat region of a nearly extreme Reissner-Nordstrom with the deviation from extremality measured by this mu. So here we did this for the reference solution, phi is minus 2 kappa RT, but this can be shown to be the case for an arbitrary phi with mu positive. So to say it again, the end message here is that the nonlinear solution obtained from the positive mu perturbation of ADS2 curves S2, when you take back reaction fully into account in electrovacuum Einstein-Maxwell theory, is just a near extreme Reissner-Nordstrom black hole with Q equals to m square root of 1 minus mu over 4.
Achilleas, what fixed the boundary condition that you only let it grow like R, this perturbation? Why can't you build the rest of the throat using bigger perturbations?
So this is precisely what we're doing. All the linear solutions around Bertotti-Robinson grow like R. That's the linear solutions around Bertotti-Robinson. When you begin back reaction, you produce other solutions. You begin to build the asymptotically flat region. But here I'm solving only the linear equations around Bertotti-Robinson, and so they all grow like R. But I am precisely saying that once you allow back reaction to take place, you will be adding all of the remaining terms in this kind of limits, which would build the entire asymptotically flat space-time, the Reissner-Nordstrom black holes.
Okay, thanks.
Yeah. Are there any other questions? Again, please interrupt at any point. This is supposed to be very simple, but somewhat confusing. Yeah. Okay. So we've learned, we've understood what the linear solutions around Bertotti-Robinson mean in terms of their backreaction. What they mean is they build the asymptotically flat Reissner-Nordstrom or extreme Reissner-Nordstrom, depending on whether mu is for those linear solutions is 0 or positive. So mu can be thought of as a kind of local diagnostic. If I only tell you what is the local geometry around the Bertotti-Robinson, that is, I give you the background and the linear perturbation, you can detect whether I'm doing extreme Reissner-Nordstrom physics or near extreme Reissner-Nordstrom physics by computing this invariant quantity mu. Here, let me also explain a little bit the diagram on the right-hand side. So here is a plot of a Penrose diagram of the ADS2. You have the two time-like boundaries, the vertical lines here. The Poincaré coordinates, T and R, cover a big patch like this triangle here, whereas this tau rho coordinates, so-called Rindler patch, is given by a smaller triangle which doesn't quite reach the other boundary, like this one here. So this particular coordinate transformation situates the two like in this picture, where the smaller triangle sits in the lower corner of the bigger triangle. Okay, but this is a picture of ADS2 with its time-like boundary present, whereas whenever it's connected to the asymptotically flat region, there is that scribe plus that needs to be attached. And so let me think about this problem and define what I call the connected ADS2 cross S2 to be just that geometry which you obtain by adding an Anabasis perturbation, either the mu is equal to 0, 1 or mu is positive 1 to Bertotti-Robinson. So this connected ADS2 is useful in that you can do Reissner-Nordstrom calculations within it and get correct results that you would expect from Reissner-Nordstrom physics. So this connected ADS2 can also be thought of as alternatively as a choice of appropriate boundary conditions whenever you do an ADS2 calculation. So let's see an example of that. Consider, for example, that you want to do a matter backreaction calculation like the one I was beginning my talk with, where you throw in some matter pulse of size epsilon. So you add to the Einstein equations a matter source like this, and it's an ingoing pulse where V is this T minus 1 over our coordinate, size is epsilon. Now for small epsilon, we can find an order epsilon perturbation, H mu, around Bertotti-Robinson, which will solve those linear Einstein-Maxwell equations with this matter source on the right-hand side now. So the solution is given by, well, the zeta component of it at least, is given by this equation here. And so unsurprisingly, you can see that both before the pulse for V less than V0, as well as after the pulse for V greater than V0, the solution is of the type I was telling you before about when I just reviewed the vacuum solutions, the electro vacuum perturbations. So it is a 4-parameter family of solutions. There are some parameters here. So now the question is, what are the correct boundary conditions? How am I supposed to set these constants if I want to do a calculation where I think of this ADS2 as being connected to the exterior of the throat and connected to an asymptotically flat region of a Reissner-Nordstrom black hole. So I'm throwing in that pulse at V is equal to V0. And so the naive thing would be to say that before the pulse, the solution is just 0. There's nothing before the pulse. That's the naive causal boundary condition that you would be using. But that's the wrong boundary condition if you're not thinking about ADS2, but you're thinking about the connected ADS2. So if you're thinking about the connected ADS2, namely it's connected to extreme Reissner-Nordstrom, let's say, for V less than V0, then you need to choose that before the pulse for V less than V0, H theta theta was not 0, but it was that Poincaré Anabasis solution that begins to build the extreme Reissner-Nordstrom. So H theta theta is equal to 2R. This is the correct causal boundary condition for the connected ADS2. So if you do that with this boundary condition, then after the pulse for V greater than V0, the solution is given by this equation here. So HZ is now this 2RPs minus this. Now, why is that great? The reason this is great is because this solution, so the solution before has mu equals to 0. That was because we're saying we begin with an extreme Reissner-Nordstrom. But the solution after the pulse for V greater than V0, if you compute mu for this solution here, now it's 4 epsilon. So mu now is 4 epsilon. That's great because this positive mu solution can be mapped to a Rindler Anabasis. So you can do that map to the Rindler coordinates, tau rho, for example, where H theta will be 2 times rho plus kappa, and kappa is the square root of epsilon. And that we know is, its backreaction will build the near extreme Reissner-Nordstrom black hole, where Q is no longer exactly M. Notice that this would not be true. You would not be getting this picture if you had chosen that wrong boundary condition where before the pulse, you just have H theta equal to 0. If you pick H theta equal to 0 before the pulse, then after the pulse, you will just have this piece, which is still a mu is equal to 0 perturbation. So that doesn't capture the physics that you expect. The physics that you expect is shown in this kind of diagram on the right-hand side. So now I'm using a dotted boundary on the right-hand side. If you see, trying to emphasize that this is ADS2 is connected, so that boundary is not there. Actually, it's connected to the asymptotically flat region. And so the physics picture that you expect is that if you throw in a pulse that has arrived in the near horizon region like that, like an all pulse like this, then after it, you expect this horizon. So this line here is initially identified with the extreme horizon of Reissner-Nordstrom. This horizon shifts, and now you have this shaded region being the exterior of a nearly extreme or Reissner-Nordstrom black hole. So you want this picture to happen. For that picture, the boundary conditions are like this. So defining the connected ADS2 like that, namely not just ADS2, but also including Anabasis perturbations on it, we get an ADS2 calculation that is consistent with Reissner-Nordstrom physics. Namely, if you throw in a pulse of energy epsilon, small, into an extreme Reissner-Nordstrom with Q equals to M, you get the horizon to shift and the black hole become near extreme with Q equals to M times square root of 1 minus epsilon. All right, so this is the end of part 1, and it's a good place to summarize. So in part 1, what we did is we defined these two things. One is Anabasis. So Anabasis is just backreaction that destroys ADS2 boundary and builds the asymptotically flat region of extreme or near extreme black holes. There's a local diagnostic to it that the Sl2 invariant quantity mu that will tell you whether you are in the extreme versus the near extreme. Then we also define this concept of a connected ADS2, which is simply the geometry that you obtain by adding these Anabasis perturbations to the boundary, to the background ADS2. Or alternatively, it can be thought of as using the correct boundary conditions for doing a consistent backreaction calculation only within the throat. All right, so are there any questions at this point? It's a good point to have questions, because otherwise I'm going to move to part 2. Okay, I guess it was all very clear, so we can move to part 2. Good. So part 2 is based on this other paper that came last December with Grant Remen. And this is the part where I will discuss the accidental symmetries. So, okay. So let's begin by setting up some notation. So the schematic notation I will use. So this is about accidental symmetries of the linearized Einstein equation near extreme horizons. And so the notation I will be using is I'm going to think of the linearized Einstein equations as a linear operator acting on the perturbation, which I'm going to denote by H, simply H here. The linear operator I will just denote by this curly E here for the Einstein equation. And what also enters in this equation is the background spacetime. So that will be denoted by G bar. So for example, the background could be the Bertotti-Robinson spacetime, and it will be in the actual calculation that I will do. The perturbation H is, for example, the phi solution that I was talking about before, the ABC solution. And so then the linearized Einstein equation is just this equal to 0 in the electrovacuum case. All right, now I will also consider doing diffeomorphisms. So if imagine that you do this finite diffeomorphism where you send TR to TR plus lambda times this vector field with components psi t and then CR. This will transform the background G bar to G bar of lambda and the perturbation H to H of lambda. Okay, so that's just a finite coordinate transformation. And by general covariance, we know that if you do this coordinate transformation, then for arbitrary lambda and xc, this linear Einstein equation will still be satisfied for this G bar of lambda background and this H of lambda perturbation. So this is an equation that is still true after the coordinate transformation. This is just a statement of general covariance. So now we know that this is true, and we can expand it in lambda, and it will therefore produce equations which have to be true order by order in lambda. So here's an expansion where we have the background at lambda equal to 0 and the perturbation at lambda equal to 0. And then you have the order lambda piece of that linear Einstein equation, which also has to be equal to 0 by itself. And then there are order lambda squared corrections. Okay, are there any questions about this notation? This is all schematic for the linearized Einstein equations and the way we're going to think about it. Okay. So, all right. So now imagine that you start, before you do the coordinate transformation, the diffeo, imagine that you start with a linearized solution of the Einstein equation. Namely, you start with the G bar 0 and an H of 0, which solves this linearized Einstein equation. So this guy is 0. Well, then the order lambda piece itself will have to be 0. And that's what equation 1 here denotes. So let's look at this equation a little bit and think about it. So there are two terms here. There are two terms in this equation. And if you think about it, what does the first term represent? The first term represents you holding fixed the perturbation. So H is at lambda equals to 0, but having done a linearized diffeo on the background. That's why G bar depends on lambda, but we're taking this lambda goes to 0 limit, first derivative, that's a linearized diffeo. Whereas in the second term, you're doing the opposite. You're holding the background fixed, so you haven't transformed the background, so G bar is at 0, but you have acted with a linearized diffeo and transformed the perturbation. As I said, this equation 1 has to be true. It is true. It's a consequence of general covariance at first order in lambda. And so these two terms will, for arbitrary lambda and arbitrary generator xc of the diffeo, will have to be canceling each other. So contributions from these two terms will have to add up to 0. But the question I want to ask in this talk is, what if we impose the strong requirement that each of the two terms in equation 1 vanishes on its own? So each of the two terms vanishes individually. So let's demand equation 2. Equation 2 is demanding that the second term vanishes. That also will, of course, imply that the first term vanishes. So the demand of equation 2 is that you're looking for diffeomorphism C, generated by Xi, which are such that you're transforming solutions of the linear equation around the fixed background amongst themselves, and you're getting still solutions. So h of lambda now is solving the linearized is solving this equation. So what will, first of all, are there such solutions, and what could those solutions, how we could think about those solutions? So the first thing to understand is that there are, of course, some solutions which you could call trivial. So these are all the diffeos which are actually isometries of the background. So if you use an isometry of the background, then g bar of lambda is equal to g bar of 0. So that's the definition of you having done just an isometry. And then the first term trivially vanishes, because the first term becomes just the background, just the equations before you've acted with diffeos. So the first term here then becomes this guy, the order 1 equation, and therefore it vanishes identically, and hence the second term also vanishes. So you will find that this is indeed the case whenever you have used a linearized diffeo, which is actually an isometry of the background, and you have acted with it on H. So these are like the Sl2 isometries of the Bertozzi-Robinson background. But if you have any other solution of this equation too, then that's non-trivial, and that's what we call an accidental symmetry. So any other coordinate transformation or linearized diffeo that you do, which transforms solutions H of the linearized Einstein equation around that fixed background amongst themselves, we'll think of as an accidental symmetry. Okay, so this is the general picture. And now let's look at the specific example. So the example is, again, where we just use the linearized Einstein-Maxwell equations in vacuum now. So we're looking for electrovacuum equations. We plug in for our g bar of 0 the Bertozzi-Robinson solution. And let's suppose that we begin with an h, there shouldn't be a bar here, with an h of 0, which is that nu is equal to 0 solution, the Poincaré Anabasis, where phi is just a times r. So this is a solution around Bertozzi-Robinson. So if you begin like that and you look for all of the solutions of that equation that defines our accidental symmetries, so that's an equation for the vector field Xi that generates the diffeo. You find that the solution is given by this equation. So Xi is, so we're always within spherical symmetry. So Xi has only t and r components. This vector field can be written like that, with epsilon of t being just that arbitrary cubic polynomial in T. So you can see here that we've got precisely that kind of picture that I was previously explaining in general terms. So there are 3 solutions here, E0, E1, and E2, which just correspond to the Sl2 killing vectors of ADS2. So Xi0, Xi1, and Xi2 here are killing vectors, are the Sl2 killing vectors of ADS2. Therefore, we expected that those guys will be discovered as solutions of that equation, because they are isometries of the background, and therefore they are guaranteed to rotate H of 0 into an H of lambda that will still be a solution. But there is a 4th solution here, E3. E3 parameterizes a 4th solution, which is non-trivial anymore, and therefore it deserves that name of accidental symmetry. So the other reason to call this accidental symmetry is because they enlarge the Sl2 symmetries that you expect to be there. I thought there was a question.
Yeah, can you remind me again? I got confused all of a sudden. So if you were just treating the space-time as a metric in its own right, then you would consider all these solutions equivalent if they're related by a diffeo, right? The thing that lets you treat them as different solutions, even though they're related by diffeos, is because secretly you're always maintaining the connection to the distant far region, right?
So, so not exact. So we are talking about doing diffeos on something like a perturbative solution around a fixed background. So it's not a diffeo that you do on a nonlinear solution, and therefore you think that it's the same solution before or after. So in particular, you would not a priori expect that there is anything more than the isometries that would lead to a solution. So if I asked you, does this equation 2 have any solutions to begin with? And if you were not solving this near extreme horizons, you would not expect anything more really than the isometry.
Right. So the point is, as a result of 2, you don't have to do the diffeo to G bar. You only do it to H. That's why they're different solutions.
Right. So 2 asks that you do the diffeo only on H.
Yeah, I forgot that. Okay.
Whereas if you do it also on G bar and then you add the 2 pieces together, then you're guaranteed by the general covariance that you will get a solution when you add them. So equation 1 is always trivially true. That's the statement that you can do diffeos on nonlinear solutions, and that's the linearized version of that statement. So that equation 1 is true for arbitrary diffeos. But equation 2 is a very strong requirement on your diffeo. And the only thing that you would a priori expect to be true for any background is that it's true for the diffeos which are isometries of that background. But for this near extreme and near extreme backgrounds, there are more solutions, and there is this guy, for example, Sl2, the accidental symmetry, the non-trivial accidental.
So when you act with the accidental symmetry, you keep the background metric fixed. You just act on H to get a new H.
Correct.
That's the key thing.
That's the key thing. Yeah, that's the key thing. So you might want to say that that's not a faithful diffeo because you don't act on the background. You only act on the perturbative solution. So it depends on your point of view. But yes, this is what is happening here. So you think of the background as fixed, and you only act with those diffeos on the linear solution. So you really take seriously this equation here, and this is the equation that you solve. You think of this linear equation as an equation on H, and you ask which diffeos, which coordinate transformations of H will map solutions to solutions. And you discover that those are obviously the isometries of the background, G bar, but there are more. And the more is the accidental symmetries. Now, this happens only when you're near extreme black holes. I have no guarantee that this would ever produce, that there would be any accidental symmetries around other backgrounds. But for extreme near horizon space-times, there are. Okay, yeah.
Yeah, thank you.
So this is confusing, so yeah, please ask questions. So good. So we've discovered that even in this electrovacuum situation, where we're just solving the electrovacuum equations, but because we are around that Bertotti-Robinson background, we find that there is an extra symmetry. There's an accidental symmetry. And here it's parameterized by this extra vector field C3. So what is that C3? So what does C3 do? Well, given part 1, we, after thinking a little bit, we have to be able to identify what C3 does. So what C3 does is it relates a mu equals to 0 solution. Remember, in this example, I'm starting with phi is equal to AR for the initial solution before the diffeo. That's a mu equal to 0 solution. What C3 does is it turns on mu. So that's why it's there. Well, that's what the accident is. That the accident is that you can turn on a little bit of deviation from extremality, and then your near horizon spacetime is still ADS2. Therefore, you would expect perhaps that this is there. And you can see this by just computing what's delta mu for this general solution C here. If you compute that delta mu, you will find that it actually contains E3 and only E3. So delta mu is given by this E3 constant. So whenever E3 is turned on, that is whenever C3 exists, you are changing mu. And so that's the correct way to think about what accidental symmetries do. What accidental symmetries do is they enlarge the possible mappings that you can have among solutions of the linearized Einstein equation around S2 cross S2 in this case.
And I see, Achilleas, can I ask a question?
Yes, please.
So I see this is the delta mu is proportional to a squared. So if you start with a b solution, for example, you can't turn on a mu. Oh, sorry.
If you start with a B solution, so to only B, so A and C are 0, then you have already mu turned on, and you can change mu. You can most likely even set it to 0, go in the other direction. So I've started with this solution, or the A solution, phi is equal to AR. If I've started with a B solution, I would be starting with a mu positive solution. And then again, I would expect that once you solve this, you will find those other linear solutions which turn mu off, and you go back to the exactly extreme Anabasis perturbation.
I see. So it's generic. So generically, you can go between mu equals 0 and mu equals some
Right.
final
Generically, what the accidental symmetry will do is anything that there is to do beyond Sl2. So so there is Sl2 isometries, and all they do is they turn on and off A, B, C, the 3 parameters. But remember, they can't change mu. So Sl2 isometries cannot change mu. Mu was an Sl2 invariant. Whereas the extra accidental symmetry, what it does is it does this extra piece, it changes mu. And so now you're allowed to move beyond mu orbits of the Sl2 by this extra accidental symmetry. So this is the kind of picture that I want you to have in mind. Exactly. So this is what I'm writing here.
Okay, I think with this, maybe I asked you in the past this, but so another way you can change mu is just increase, for example, the amplitude of your linearized solution. But that cannot take you from mu equals 0 to some finite value, right? So that's the difference here.
Exactly. Yeah, that's the difference here. So when I say change mu, there is only really one thing to do here at the linearized level: either turn it on or off.
Right.
Because as you say, for linear solutions, if you just change mu, magnitude of mu, then you haven't done anything non-trivial really.
Right.
So yes, in the selector vacuum case, where amplitudes are arbitrary, changing mu really is equivalent to saying that you're turning it on or off. Yeah. So indeed, so the big picture is that you have the linear solutions, which are ABC solutions, and you can rotate ABC by Sl2 isometries, but that does not allow you to move between different mu orbits, namely turn on or off mu. That's what the accidental symmetry allows you to do. Good. So that.
Achilleas, does that algebra close, or will you generate all of the higher L's if you now try to use the Sl2?
Yeah, that's a good question. So you can, these 3 guys generate the Sl2 algebra, but once you have a 4th guy here at the level of just computing algebra of these vector fields, you can generate all of the remaining Virasoro elements of the larger algebra that contains Sl2. But those are not gonna, those other, this is just at the level of commuting vector fields. These other vector fields will not be symmetries of this equation. They will not satisfy equation 2. They will not, they don't turn out at this equation. And I have no reason to expect that they should have. So this is a strong requirement that you remain on solutions of the Einstein equation. If you want to allow yourself to go off shell, then you can think about this stuff. And in holography, this would be thinking about arbitrary large diffeomorphisms of ADS2, basically. We can talk more about that later. I didn't include any of that in this talk because I thought there wouldn't be many holographers in this. But yeah, so if you allow yourself to go off shell, you don't demand that you continue to solve the Einstein equations, the classical Einstein equations, then you can think about generating the rest of the Virasoro. Yeah. Are there any other questions? These are all very good questions. So let's see, how much time do I have? Yeah, I don't have too much time, but I don't have too much else to say either. I just want to show you what kind of impressive outcome you can have if you go beyond this setup of electrovacuum equations. So we're in electrovacuum and there is Birkhoff's theorem. So that constrains us to only talk about this kind of non-propagating degrees of freedom. So degrees of freedom where you just turn on or off charges like the deviation from extremality, for example. To go beyond that, it's, to ask the question, can you use accidental symmetries to turn on anything else other than this type of charges of black holes? Namely, can you turn on any propagating degrees of freedom? And we've done one calculation of this sort, and we found that the answer is yes. So imagine that you add some matter, and now on the right-hand side of that equation where we used to have 0, there's a source T. So this is again schematic for the linearized Einstein equation where there is a source term on the right-hand side. So for example, imagine that you have a source which is obtained by, obviously T cannot be arbitrary, because if you do arbitrary transformations and you call whatever you get on the right-hand side T, you haven't done anything. You have to impose equations of motion on T. And so the simplest thing to think about is to get T from the stress tensor of a Klein-Gordon scalar phi that you put on that background Bertotti-Robinson. So if you think about it that way, then the Klein-Gordon equation, box phi equals to 0 on Bertotti-Robinson on ADS2 cross S2, has this as its solution. So this is the most general spherically symmetric solution on ADS2 cross S2 for a massless scalar. There are two arbitrary functions, phi plus and phi minus, of u and v, which are this T plus minus 1 over r coordinates. So the question here now is, could I get this source T on the right-hand side by acting on the electrovacuum initial solution, phi equals to r, using some kind of accidental symmetry? Would that be possible? And the answer is yes. So here I've displayed what we found for this question. So we found that indeed, if you define capital F plus minus by these equations here at the bottom, and you act with this vector field C on the electrovacuum perturbation phi equals to r, so initially the perturbation just satisfies the sourceless equations, then you generate an arbitrary source of an arbitrary Klein-Gordon field by this equation. If you think about this, it's quite impressive. So you're saying that you can turn on an arbitrary propagating degree of freedom as long as it's within this Klein-Gordon setup by acting with a coordinate transformation on the empty background perturbation of the near horizon of extreme Reissner-Nordstrom. Okay, so let me summarize. So what is accidental symmetry? So this is a summary of part 2. What is accidental symmetry? Accidental symmetry is a coordinate transformation that acts on the perturbative solution of the Einstein equation, and only on that perturbative solution, not on the background itself. And near extreme black hole horizons, it is able to map solutions amongst themselves. So, for example, in the electrovacuum case, we saw that this allows you to turn on deviation from extremality. Whereas in the case where we've added matter, Klein-Gordon matter, we saw that this allows you to turn on an arbitrary Klein-Gordon source. And I'm going to leave you with this remark, which might not mean anything to people who are not coming from the HEP-TH community. There is a way to, think of those accidental symmetries as an on-shell version of so-called large diffeomorphisms of ADS2. This can be made at least, this can be made precise, at least in the context of this model of two-dimensional gravity that goes under the name JT for Chekhov title. All right, so this is just a remark that I can talk more about if there is interest. So this is the end. Thank you.
All right, thank you for the fantastic talk, Achilleas. We have plenty of time for questions, so just unmute yourself. Go ahead and ask.
So in the dream of finding what the Virasoro transformations do when you connect to the far region, I think you've shown pretty conclusively that for electrovacuum Reissner-Nordstrom, you don't get the whole Virasoro, you only get L2. But for NEC, maybe there could be more. Are you going to try Kerr next? Is that the next step, or?
Yeah, good. So, right, for people who don't know what NEC is that near horizon of the extreme Kerr, the thing that I had in the first slide, the generalization of Bertoldi-Robinson to the case where there is rotation. So that's what NEC stands for. And indeed, because NEC is now, even if you restrict it to axisymmetry, there is no Birkhoff's theorem to constrain you like this in the vacuum Einstein case. So you could expect that this calculation with the matter source is a proxy for what would happen for NEC. And indeed, that's what I expect. And we've looked a little bit into this. We're working with equations, but NEC is complicated and we don't know what the answer is. But it is totally expected that the answer is something like this slide here, namely propagating axisymmetric gravitational wave solutions around NEC could be mapped by a symmetry like this onto an Anabasis perturbation of NEC, namely a perturbation that is just empty extreme Kerr. We haven't shown that yet, and we're not close to showing it either. Equations for NEC are difficult because the theta part doesn't decouple from the TR part so easily as it does here within spherical symmetry. But yeah, I mean, it is expected, at least I expect that it is true, but something like this is true, namely axisymmetric propagating gravitational waves of NEC are related by a symmetry like this to the Anabasis perturbations.
Without the scalar, right? In vacuum.
Yes, in vacuum, just vacuum Einstein equations. Yeah, the scalar here is as a proxy for what happens for that axisymmetric sector of vacuum Einstein around NEC.
Yeah, that would be really interesting. Thank you.
I mean, I should say that we know that those axisymmetric propagating solutions around NEC exist. So those propagating degrees of freedom exist. What we don't know yet is whether they can be mapped by symmetry like that onto the just the Anabasis perturbations. That's what we want to show. That they exist as physical degrees of freedom around NEC, that is known. So you don't want to do this in Newman-Penrose formalism because that's doing a lot of gauge fixing and it's not helping you. But doing it in metric perturbation formalism should be possible. That's all I can say for now.
All right, do we have any other questions?
So,
All right, go ahead, Sean.
yeah, just, I mean, this, right, as a relativist, right, I mean, they're thinking about, acting with the diffeos only on the solutions and not on the metric. I mean, it's kind of puzzling what the physical meaning of this is. Right, I mean, from the point, I mean, has something like this been discussed in the past somewhere?
Yeah, so indeed, as a relativist, you might be hesitant to even call it a diffeo, right? Because you're doing a coordinate transformation not on the whole thing, but only on the linear perturbation. That said, the analogy with JT, well, when you actually look at it, and we can talk in more detail about that, is like that. So when you ask, is there anything like that in the literature? That's what there is whenever people actually talk about large diffeomorphisms. So what are large diffeomorphisms? So large diffeomorphisms, for those who don't really know, they are just honest diffeomorphisms actually, which, because usually of the presence of a boundary, because they don't fall off fast enough in the boundary, they do something non-trivial to the boundary, and therefore, they become large, they become non-trivial, they become physical. So those large diffeomorphisms of ADS2 or of ADS3, when people discuss them, they can sometimes put them on shell in the following sense. They impose some boundary condition near the boundary. So here that would correspond to saying that you begin with, say, this phi equals to AR. And then you do the diffeo, and yet you demand that you keep that boundary condition of phi equals to AR the same, both before you have acted with the diffeo as well as after you have acted with the diffeo. So when you present it like that in a situation where you actually have a boundary, a time-like boundary, it doesn't sound as dramatic because you have still faithfully done the diffeo everywhere in the bulk. But if you demand that you keep that boundary condition the same, then that's the equivalent of what we have done here. Because that's basically like saying, like demanding that the first term here is 0. Namely, these metric perturbations H of 0 are the proxy for those boundary conditions on the ADS2 boundary. So think of them as proxy for that. Then, if you say that you've done a diffeo on the ADS2 on the background, so G bar now goes to G bar of lambda, but you keep the H, or namely the boundary condition on ADS2 boundary, the same, then you're demanding that this first term is really 0. So that's how the analogy with the JT story goes through. So when you ask, has this ever been done in the literature? My answer is yes. Whenever people, say in JT, claim that they're going to act with a large diffeo, but they're going to keep the boundary condition on ADS2 the same, they are doing that. They are restricting all the diffeos that are allowed to only the on-shell large diffeos of ADS2. Yeah.
So it's been done, but in a different language.
It's different language. Yeah, it's different language.
Thanks.
Yeah.
All right, well, let's thank Achilleas again for a great talk. Really enjoyed it.
Thank you.
I'll stop the recording and hope to see you all next week.